Hey guys, I'm going to walk you through number 1 and number 2 here for this activity that you're working on tonight, and then tomorrow you're going to finish it up. So please make sure you read the entire scenario here, what we have going on in this murder mystery, and we're trying to actually make the learning a little bit fun here because it's so applicable to real world applications. So there's lots of things you can do with logs in the real world. So read number 1, basically want to set this up as an exponential, and then number 2 says, well, now let's model it with Newton's law of cooling. So I want to walk through both of those with you and kind of show you how you end up with the same thing. So number 1, y is equal to a times b to the x plus k, and in this situation, k is your asymptote, which is just going to be the environment's temperature. So the body cannot cool below 17 degrees Celsius because that's the temperature's environment, or the environment's temperature, sorry. Now, we have 2 data points, 0, 27, and 1, 24. So we're going to approach this very similar to the logistic modeling that we've been doing, where if I know I have an exponent of 0, it essentially makes this go away. The b kind of just goes away. It becomes a 1. So now I only have one unknown of a. So when I subtract 17 over, I get a is 10. So write everything else out again, replacing a with 10, and now we can solve for b. Now we have another data point, 1 and 24, where now I don't want my b value to disappear. I want to be able to solve for it, so I want to set it up like this. So I would subtract 17 from both sides, and then I'm going to end up with b is 7/10. So b is going to be 0.7. So this model would look like this, 10 times 0.7, and it's going to be to the x, and that's how we would model it. Oh, I need my asymptote there. All right, so that's how you could model it using sort of like the basic exponential equation. Now, we've been asked to also model it using Newton's law of cooling. And recall what this is. You have the temperature of the environment, kind of the same thing we have up here. And then we have a difference between the initial temperature and the environment's temperature. And then that's multiplied, that's kind of like a coefficient of e to the negative kt. Now we need to find k. So we basically want to figure out what we can plug in. Well, the environment's temperature is 17. The initial temperature is going to be 27. Again, this would be a 17. And then what do we have for, I'm going to go ahead and call this x because it is time. So we have an x and we have a y, but remember we don't really want our k to disappear, so I don't want to use a 0 here, so I'm going to have to use the 1 and the 24, and that makes perfect sense. So multiply by 1, and then I replace this with 24. Okay, so our only unknown here is our k, and we're going to solve. We're going to divide by subtract 17. We get 7 here. This is simply a 10 e to the negative k times the 1. So to find our k, we need to use natural log. I need to isolate the power, so I'm going to divide by 10 on both sides, and I'm going to get 7/10 here. So we have our power equal to something on the other side. So to solve this, I'm going to take the natural log of both sides so that I can bring the negative k out front, basically making it a multiplication, and I'm going to write this as 0.7. Now to find, this is just 1, to find k, I'm just going to divide by negative 1. Negative 1. So k is just going to be the negative ln of 0.7, like that. All right, so let's plug everything back in and kind of see where we are. So we have temperature based on time is equal to 17 plus, and I'm going to go ahead and just do a 10 here. That's always just going to be a 10. E, and then I have a negative negative. So a negative negative is going to turn positive, so it's just going to be ln of 0.7, and then that's going to be multiplied by x. And be very careful, it is not ln of 0.7 times x, it's ln of 0.7, get that value, times x. So 2 very different things. All right, now, so the question at hand is, how does this Newton's law of cooling match our exponential model up here. So let's kind of move some things around in this one. So I'll just call it Y for temperature based on time. I'll move the 17 to the back like this one is. I still have my 10 here. I have E to the ln of 0.7 times x. So E is raised to all this. So the question is really, let me scoot this over, plus 17. The question is really this. We have a 10 in both. We have a 17 in both being added. The question is, how does this equal 0.7 to the x? Well, let's look at it. So I have E to the ln of 0.7 times x. So I could rewrite this basically and say that all of this will simplify down because of the E to the log base E of 0.7. It simplifies down to 0.7, but I need to deal with the exponent here. So this is actually able, I can actually do that. That's something I can do. Now here's why. If I have 2 to the 5th power, well no, let's go with the 6th power. If I have 2 to the 6th power, do you guys remember I could rewrite that as 2 squared to the 3rd power? So that's essentially the same thing I'm doing here. So now you can see that I have E to the ln of 0.7 raised to the x. This entire piece is going to simplify down to 0.7. And it's because E to the log base E of 0.7, which is what we really have here, is just equal to 0.7. So it's one of our properties. So I proved that it does simplify down to the 0.7 to the x power. Okay, so they are indeed the same thing. I just kind of wanted to show you that. From here on out, I would suggest you kind of go back. Let me kind of write this out for you. I would suggest you go back and rewrite this as 17. You're going to have plus, and then you're going to want to be changing this right here. It's always going to be minus 17, but you're going to want to use a different temperature at times. This will always be 17, and then I have E to the ln 0.7, and then in parentheses, of course, times T. So I would use that model kind of going forward, but they are indeed the same thing. So hopefully that helped you out, kind of exploring both setups, and I mean, it's confusing sometimes as to how you approach these. So hopefully that helped you out. Make sure it makes sense to you before you come to class tomorrow, because you're going to finish this up with a partner and it will be graded. So you all have a great day.